Hello, everyone. Welcome to the Mindscape podcast. I'm your host, Sean Carroll. If you are a working cosmologist and you're studying the cosmic microwave background, in particular how density perturbations in the microwave background grow into galaxies and large-scale structure, etc., one of the first things you have to learn about is matter falls in to some overdense region and then photons stream out. And the photons streaming out damp the oscillations and the growth of structure in that pre-CMB era. This phenomenon is called Silk damping, after today's guest, Joseph Silk, who first wrote about it in 1968 in a paper on galaxy formation and the cosmic background radiation. Pretty amazing when you think that we only discovered the cosmic microwave background radiation in 1965. Joe Silk has gone on to be a leading theoretical cosmologist for decades now. I've known him for a long time, and for example, after we discovered the anisotropies in the cosmic microwave background from the COBE satellite in 1992, it was clear that Joe Silk's group at Berkeley at the time was one of the very small number of leading places which was training up young people to tackle this new set of puzzles. So it was slightly surprising to me when Joe recently gave a colloquium at Johns Hopkins, and it was not about recent wrinkles in cosmological theory. It was a sales pitch for going back to the moon and building telescopes there. Now, obviously, there is a relationship here. Any working cosmologist wants more data, better data, and the moon provides an excellent place to build telescopes and get more cosmological data. But the thoroughness of the case that Joe made and the interest in all the different aspects of it, I thought was very impressive. In fact, I learned thereafter that Joe has a new book out called Back to the Moon, The Next Giant Leap for Humankind, where he takes very seriously the idea that not only should we travel back to the moon in our little spaceships, we should put people there, have a settlement, and do science. He makes a very explicit case for the different kinds of telescopes that you can build and also for other benefits of being on the moon, including mining rare earth elements and things like that. So this is a very fun conversation because it's a intersection, right, of science issues. You know, why can't we just build a big telescope on Earth or in orbit or whatever? What's so special about the moon? But also practical, technological, and political issues. Who's going to do this? Do we have the money? What is the case for it for people who don't necessarily care a lot about modern cosmology? I think it's kind of persuasive. I think that, the case is actually pretty darn good. Opinions may differ. That's perfectly okay. But it is something that the human race is going to be confronted with the possibility, the opportunity to do in the near-term future. So I'm happy that we're thinking about it at a high level. Let's go. Joe Silk, welcome to the Mindscape podcast.
Thank you for inviting me.
I was in the audience for a colloquium that you gave at Johns Hopkins, where we are colleagues, and I've known you for decades now as a famous, accomplished theoretical cosmologist, and here you are advocating to travel to the moon. So I presume there is some story there, or at least there's some, I know there's an intellectual connection in terms of the science that can be done, but how did you in particular decide that building telescopes on the moon was what you really wanted to put some effort into?
Well, I was getting very frustrated with the progress in cosmology that I was seeing around me. My colleagues have made immense advances in cosmology when I began in the field, which is, I guess, maybe half a century ago. I hate to think of it, but there were uncertainties in measuring parameters such as the Hubble constant, other things. It's enormous, 50% uncertainty. And we live with that. We spent our early careers debating, issues of 50% uncertainty, factors of two unknowns.
Yeah.
Suddenly, over the past decade, as we've brought in much more precise surveys, especially of distant galaxies, we've made enormous use of the microwave background also as a cosmological tool, the fluctuations in that background. Our errors, our systematics now have dropped to maybe 2%. But it seems that the same questions are still plaguing us. Namely, how did it all begin? And, what is the meaning of it all? The universe does seem to be accelerating. We've learned that from this enormously improved data. But what does that mean? Where does all that come from? And so we're hoping that with the next generation of surveys, with bigger and better telescopes, my colleagues are hoping at least they'll get some answers. But I'm very, very pessimistic because what I've seen is that over the years I've been in the field, we had this outrageous hypothesis at the beginning from Lemaitre, Georges Lemaitre, that there was a cosmological constant. The universe is accelerating at the moment. And we didn't understand it at the time. We still don't understand it. But all the recent studies converge on Lemaitre's original hypothesis, the constant. You need to see some deviations to understand the physics better, to see what's really going on. And I saw no prospect in not just the current surveys, but the next generation of surveys actually making real progress, because all we've seen is convergence. So I decided that we're going to do something radically different to make a breakthrough here. And eventually it seems that putting telescopes on the moon is going to be the way to do that. Over the long term, that'll be the next step forward in cosmology, I think.
I mean, it's a fascinating answer, which I didn't anticipate. So it all comes from the cosmological constant problem and the issues that it arises. I mean, you're right that cosmology is often inspired by these very big questions. Why are we here? How did it all begin? And then the working cosmologist ends up measuring the amplitude of density fluctuations to some percent or something like that. I mean, do you think that there is this kind of prospect for answering those bigger questions if we just get better telescopes?
Well, let's see. It's more than just the cosmical constant, because we have to go back also to the beginning, which is now pretty much to everyone in the field, the theory of inflation. It's the most significant advance in cosmology since the time of Georges Lemaitre in basically, a century. But we have no proof. We don't understand how inflation really began. Now, there is a fascinating hypothesis that we're trying to test, namely that as inflation came to an end, it generated gravitational wave modes that left their imprint on the microwave background. So we have many experiments, beautiful experiments set up to look for those. And no doubt they will give us some answers in 10 years. But the problem is that there is absolutely no guarantee they will achieve success, because the predicted value of this distortion is totally uncertain. If we're lucky, if we're optimistic, they'll find it. They'll find the missing proof. But the chances are it could be almost at any level. And so my view is, why don't we do some cosmology with a guaranteed return, which will tell us the answer? And so that's what really drove me towards this next stage, which I can tell you about, to do with doing something on the moon.
Yeah, no, we'll definitely get there, but I'm just intrigued to ask one more question along these lines while I have you here, which is, what is the probability that you personally would put on inflation or something very much like inflation being true in the real world?
I would like to think it's 50%. Okay, it's such a compelling theory to me, but it also raises questions as to how it began. So for that reason, I won't go all the way to a higher probability, and it's so compelling that I wouldn't give it a much lower one. So 50%, I think, is a fair answer, which means you'll better do a lot of work to get any better than that.
That is exactly my probability. So I'm very glad that we're on agreement here. I think that a lot of our colleagues put it a lot higher, which worries me a little bit sometimes. So going back to the moon then, that's a big thing. We've been to the moon once before, the Apollo missions, et cetera. Why don't you set some context by telling us what the previous moon missions accomplished and why they ended, what's different now? It was a long time ago. It was 50 years ago.
Oh, that's exactly right. I mean, the Apollo dream, the Apollo accomplishments were marvelous, actually. They were inspired by JFK, of course. He had this driving ambition to demonstrate to the world that he could out-Sputnik the Russians, having been taken aback by that at the time. And he did it amazingly in half a decade. And the budget they put into that was enormous. It was, a significant fraction of our gross national product in the US. So we'll never see days like that again. But nevertheless, it's clear as time has gone on that we want to go back to the moon because that is our next major frontier in scientific exploration for many reasons. And if we put telescopes on the moon, I think we can answer some really incredible questions about the universe. And perhaps the biggest question of all is what was there out there before there were any stars, before there were any galaxies? We call that era the Dark Ages. And so I think we can ultimately penetrate the Dark Ages only from the moon.
And do I remember correctly reading that at the peak of Apollo, NASA's budget was something like 4% of the U.S. total budget, and now it's more like 0.4%?
That's absolutely correct. But you must remember that 0.4% is still an awful lot of money, and it's more than enough to finance the Artemis program, which is the current program to get humans back on the moon. And more than just back on the moon, but to build a space station around the moon and do many other things.
Well, let's fill in some of that because I'm not actually up on it. So the Artemis program is happening, right? Like NASA's doing it, and it involves boots on the moon.
That's exactly right. So the first goal is to get boots on the moon. And the interesting thing that is spurring this along at great intensity is China is doing exactly the same thing. They have a program to have the first astronauts back on the moon in 2026. And NASA wants to match that, and if anything, get there before the Chinese. And it's not a question of getting just anybody on the moon. Both countries announced that they want to get the first woman on the moon. Which is an amazing breakthrough. And among the astronauts in training on the NASA ESA side, there are even astronauts of color and even one disabled astronaut. So I think that's, our boundaries are changing. Mm-hmm. But it'll be much more than putting astronauts on the moon, of course, but that's the first step.
And you mentioned a space station. I've heard about this. There's the Lunar Gateway that is going to be in orbit around the moon rather than orbit around the Earth?
That's correct. So that's the next step. And the reason is that you want to go to build a facility from which you can easily land on the moon without creating too much havoc in lunar dust, etc. It's so much easier than going directly from the Earth. You have a space station with pods in from which you can send landers down to the surface. That's how we did the Apollo program, right? We sent an orbit around the moon, which dropped pods onto the surface. So it's the same idea. And from this orbiting space station, we'll be dropping that. That'll be where the astronauts reside at first. One can just make that a more homely sort of place, a safer place to live than initially on the surface of the moon. And so that's where they'll be, and we'll have pods coming down. The long-term goal of the space station will also be to launch rockets into interplanetary space, further afield, and also back to Earth, of course. So it'll be a major hub for exploration. But we'll start off in orbit around the moon because that's such a much easier place to develop.
And just to calibrate our expectations here, this is all stuff on the NASA side that is in the budget, right? This is not just a plan that they're dreaming up and trying to sell to Congress. This is the ongoing stuff is happening for this project.
That's correct. And this all comes out of the standard NASA budget. It's a small fraction, of course, not so much of the NASA budget, but of the total GDP. but this is enough to keep the whole Artemis program going for the next decades.
Are there other countries besides the US and China who are interested in this?
It's an amazing race at the moment between the primary players are the US and China, because they have so far the largest spacecraft and the largest manned crewed space programs. But smaller spacecraft are being launched by many other countries. They're driven actually by the availability in the past recent years of commercial launches, which are eager to expand their horizons for future exploitation of the moon. And so they're available and they're being sponsored but not just by NASA to develop spacecraft, but also they're available on the international scene for any country to buy a launch vehicle to use one to send stuff to the moon. But in the past 3 months alone, there have been launches by Israel and by the United Arab Emirates, both of which were unsuccessful, but they're being planned. They're going to repeat them, and they were designed to send small lunar rovers to the moon to do surveying of terrain. That, incidentally, is what we have to be doing now, thinking of, because one of the major issues is going to be how to use the moon, how to exploit the moon. And for that, we need information, and that means basically doing surveying of the moon, both from satellites and from on-site rovers.
And when you mentioned the commercial spacecraft, this is, I presume, SpaceX, Blue Origin, companies like that?
Yes, and there are probably a dozen small companies now, not just in the US, but one or two in Japan, etc., which are trying to make a commercial business out of the moon. Of course, the moon is very high on the list of tourist destinations. And so that will be another goal, as well as exploitation of the surface of the moon for resources that we can use on the Earth.
Would you go as a tourist to the moon if you could afford it?
Were I much younger, yes, I jump at the thought. But
Yeah,
right now, I don't think my mobility would get me, even though the gravity is lower, that would help a bit. But I
got to get there first, though. Yeah. So, but it's interesting because I guess that is a consequence of these private companies building their own space vehicles, is that other countries can get into the game much more easily. As long as they have money, they don't need the technological know-how necessarily.
Yeah. So what's quite amazing is that the cost is coming down rapidly of these transport vehicles that take us to the moon. The commercial industry is very good now at modest payloads of tons, a few tons perhaps. The major payloads, which are just for the moment in the domain of StarX, of NASA, of China, Russia too, which can carry tens of tons of payload, those also are rapidly developing. And the net effect of all of this is the cost per kilogram of delivery to the moon is going down rapidly. So it's a whole new ball game for doing things on the moon.
Yeah, and so let's just segue into what we want to do on the moon. I mean, obviously, the skies are dark and clear, but tell us more in some more detail. Like, what is the call for cosmology and astrophysics?
Well, before we do that, there is competition. Before we get to science, science is at the back of the queue. There's no question of that. But Let me tell you what the major driver is right now to go to the moon, and that is to exploit the moon, to do mining on the moon. Now, the mining is really, really simple to start with, okay? Because all we want to mine is ice. Amazingly, there are craters near the poles of the moon, many craters, which are in permanent shadow. They have such high rims. The sun never gets too high in the horizon because they're polar, they're near the poles, or too low. And so they're very cold. In fact, the temperature measured in these dark craters to be as low as 30 degrees Kelvin with absolute zero, just incredible, which is great for astronomers. It's also great for ice. And what was discovered a decade ago was that these craters are full of ice, many of them. So what do you do with the ice? Well, the idea is it's got two immensely important uses. One is you can break it down into hydrogen and oxygen, liquefy the two. You have rocket fuel. And then you also have oxygen for habitat use. And so suddenly we can now imagine designing, and we have energy sources, obviously, from the hydrogen too. So now we can obviously design habitations on the surface of the moon, aiming at exploiting the dark craters, permanently shadow craters near the poles of the moon. So that's the first goal. And that's a major step because that will be the key to doing everything else on the moon.
Do we know how much water ice there is?
It's hard to be totally quantitative, but our leaders, the agencies, are convinced there's more than enough to supply rocket fuel for a very long time. So that they're eager to exploit that, very eager.
But overall, maybe this is jumping ahead a bit, but if we want to build things on the moon, we are going to have to crate up a lot of tonnage of material from the Earth to the moon, right? Like presumably we can't mine iron very easily.
In fact, the lunar regolith is a very rich source of all the elements you might need to, for example, build electronics. Even you can easily make cement with lunar dust and water, and do structures on the moon. So everything is in place, and it is envisaged over the next decade or two we'll be manufacturing locally on the moon. So we won't have to ferry everything to the moon. One could do more or less anything one wants with local materials. So
okay.
That's part of the planning.
Does that include the raw materials for breathable air?
Indeed, yes. But basically, you have the ice and the oxygen so that will give us the atmosphere we need, and you can get enough inert gases from lunar regolith to mix with the oxygen to make it safer. So that's to be done.
So I want to ask more details about that, but let's get the motivation more explicit here. I presume that as an astronomer, cosmologist, you want to build telescopes. Are there specific kinds of telescopes that are especially better on the moon than just, say, in orbit? I mean, we're doing pretty well with JWST, which is not on the moon.
Right. So the problem is JWST is a pretty small telescope, really. I mean, 8 meters, it's not even that we can build larger ones on the Earth, actually. We've gone to 39 meters as the current one, large under construction. That's probably the limit. We'll never build a bigger one. The problem is that what you want to do is to ideally look very far away with your telescopes, but also look in detail even nearby with incredibly high resolution, both in terms of the spectrum and the light gathering power. And it turns out that to really do a good job of that, you need a much larger telescope than we can currently launch into space. And so let me give you the optimal example of this, which is if you could imagine building a telescope that was 1 kilometer across, and you could only do that on the moon, very hard in space too. But in principle, you could go to a dark crater and fill the crater with mirrors and combine the beams, etc. People have thought of ways of doing this. And if you could combine those beams together, and I can explain how that's done in a second, but the first point is that with such a huge diameter, you need incredible resolution. Suddenly, you could get resolution of millionths of a second of arc. That's millions of times better than you can do on the Earth, just limited by the size of the telescope, actually. And once you get that sort of resolution, you can imagine looking at nearby planets that are twins of the Earth, actually, around nearby stars tens or hundreds of light years away. And with that exquisite resolution, you could study these planets, some of which are twins of the Earth, actually. And we have no idea what's going on in those planets at the moment, but with this resolution, you could look at the cloud cover, You could look at the mountaintops. You could see the glimmering of the oceans against sunlight from the host star. You could look with spectroscopy into the atmosphere in detail for signs of life-like indicators, methane or whatever, for example, or pollution from, industrial or even nuclear fuels, that sort of thing. Tiny amounts you could suddenly see, provided you had a big enough telescope. So in some sense, a big telescope is the key to really answering one of the biggest questions we have, namely, are we alone in the universe? To me, that's one of the most exciting goals. And just to finish, you wonder how on earth you do this. Well, you go to a dark crater, which already is very cold. So it's a great place to build telescopes. It's very dark all the time. And you string your camera from the rims of the crater. Okay, and so you build telescopes on the basin to basically all focus their beam at the camera. It's sprung from the rim. And the only challenge really is to combine those beams. And that's a simple question of basically quantum physics, really, because we're finally learning. We've done this now for essentially 2 telescopes on the Earth. We now would have to do this for hundreds of them to combine beams together to make them coherent. So all these many small telescopes to give you the equivalent of one big one. But that is possible. It's technologically possible. It means developing much better beam combiners with ideas from quantum physics. But we're on the way to doing that. So I could see that in 10, 20, 30 years, a telescope like this could answer one of our biggest problems.
That's great. And just to try to dig into the details a little bit more for the audience, or maybe for me, and I'm the proxy for the audience, I know that in radio astronomy, a technique like this is often used, right, where we use different individual dishes and combine them into one big telescope. That's harder to do, more rare to do in optical or infrared astronomy because the wavelength of the light is shorter, I presume. Is that it? Is there more to it than that?
No, there's more to it than that. The other problem is the atmosphere, the Earth's atmosphere. It makes it incredibly difficult because it gives you scattering, turbulence, etc., in the atmosphere, invisible. That means it's incredibly hard to cohere these beams together. At long wavelengths, it's easier. At short wavelengths, it becomes almost impossible, which is the great advantage of going to the moon, where you have no atmosphere. And so that makes a huge difference. It doesn't mean to say it's easy to do, but it's going to make it a challenging project, but I think we can do it.
So that answers the other question I had. Is the primary advantage of the moon, I mean, one of them is obviously the atmosphere is not there, but another one presumably is that there's less gravity, so maybe it's easier to build a giant structure without it, collapsing under the force of gravity. Is that a benefit at all, or am I being fanciful?
That's exactly right, and I'm sure that this idea of using a natural crater to combine a lot of small telescopes together, that's one design option. Another one might be to build a coherent, much larger telescope than anything we can build on the Earth, because there are no winds to shake the structure. Gravity is much lower. You would be able to support the structures much more easily. So that would be another direction to go in. And we will need to discuss that in enormous detail, the designs, the pros and cons. Probably we'll end up with both approaches eventually.
Is the reason to use a single crater, if we're going to have many dishes and physical dishes and then combine them together into one effective telescope, I'm wondering why we don't just scatter them all over the moon rather than putting them in a crater, but maybe it's just colder in the crater?
Yeah, and it's also dark all the time, so that's a big difference. But it's colder, and I mean the extremes of temperature when you're not in the crater or the moon are enormous. They go from incredible heat to incredible cold, and it's very hard to design a structure that can operate, with a high sensitivity under those extreme conditions. Whereas in a dark crater, you have much more control over the thermal environment. And so it's a much more stable situation where you'd want to build your telescopes.
I was going to say maybe it's also just hard to do it in a very cold environment, but presumably satellites and existing orbital telescopes do that all the time.
That's right. And, one would be, working with robots on the moon, I'm sure, as well. So it wouldn't necessarily need a human presence right at the telescope. Certainly for installation, you might, but eventually you would not.
So you've made a very good evocative case for super high resolution pictures of Earth-like planets elsewhere. So let's let our hair down a little bit. What do you think we're going to see? Do you think we're going to see life on a whole bunch of other planets? Do you think that we'll see intelligent life?
Look, we have no idea. The problem is that we've theorized a lot over the origins of life. We simply don't understand it. There are a number of theories out there, ranging from, origins in some muddy, shallow parts of oceans, etc., life emerging onto land, etc. But, all this is just a guess. We only have one example, actually, on the Earth. We are eager to go to Mars for the very good reason. Once upon a time, that had an atmosphere, that had flowing water. It's pretty arid now. There's no evident signs of life on Mars. We haven't seen them yet. But the thought is, if we go to Mars and dig deep, maybe we'll find some dried bacteria or something, or perhaps even more that may give us clues. But right now we have nothing. Another option is there are one or two moons, one in particular around Saturn, called Enceladus, which is covered in ice. But we know that beneath that ice, there are water oceans. And we found that out by a recent mission shooting a probe in, and we saw the water splash out. Quite an amazing experience. So that ocean, cold ocean, is another place where we're going to go back to and look for life. But frankly, I can't imagine that would be, even if we found something, it would be terribly interesting from this question of life in the universe, etc. So we have to do that, of course, but I think our best bet is to look for planets that are essentially like the Earth. That is, they have rocky cores, they have atmospheres, they're not too far from the host star, which is like the sun, not too close, so they wouldn't get, they wouldn't be burnt to a cinder really on the surface. And so we now know that there are many such planets. Our best estimate is billions in the Milky Way. And so all of these are potential sites of life. But because we have no idea where the chances of life is 1 in a billion or 1 in hundreds of billions or maybe 1 in 100, it's all open, we have to look. And so the way we look is we try to get a sample of these exoplanets. And the trouble is that with a small telescope, such as the one that our agencies are planning to do life searches, like the best one that we have that came out of a recent study was a 6-meter telescope designed to get exquisite images of the atmospheres of nearby exoplanets. So it had very high resolution. It has a device for shielding the blinding light from the star, so you can actually see the planet to some extent against the star. The trouble is, with a 6-meter telescope, you have a sample of probably 20 exoplanets around the nearest stars that you could have the sensitivity to really study. And that simply is not enough. So my dream is that, with a, let's say, 100-meter telescope on the moon or an even larger one, would suddenly improve that sample from, tens, thousands of exoplanets and improve our odds of finding something interesting. So that's the reason we want to build bigger telescopes, and we can best do that from the moon. It would not be affordable anywhere else, actually.
And I know this is not exactly on the science point, but I wonder whether we really appreciate the effect it will have on our psyche and our self-image as human beings when we do find that there is life on other planets. Is it going to be are we so prepared for it? Have we priced it in, or is it going to be a shock to the system?
I think over the years we've priced this in with all our, warnings about UFOs and the like. So I think people a certain subset of the population are ready for this, I would say. Most of us perhaps are not, but
Yeah.
and the chances are, of course, if we do find something interesting, we're discussing something many light years away from us, it's hard to see any, dramatic communication.
Right. And it's very unlikely, just to put a cap on this, it's easy to imagine extraordinarily primitive life, right? Single-celled organisms, whatever. And maybe it's possible to imagine super advanced life that has gone way beyond us because they've been technological for 1 billion years now. But it's very unlikely we will find peers out there in our galactic neighborhood nearby.
That's probably right. It'll be one extreme or the other. I think I would agree with that. And the worrying thing is, of course, is that when we try to extrapolate to life around stars that have been around for billions of years longer than our sun, any life there would have had 1 billion years or so advance on the Earth for making life. The trouble is, we have no idea whether that life would have survived that 1 billion years. There are so many potential catastrophes we're going through on the Earth now that who knows how challenging that would be over longer time scales. So on the other hand, it's possible, of course, as a sort of a science fiction writers tell us, that it could be a very intriguing and highly advanced form of life. I guess we're open to this. But,
do you have a favorite answer to Enrico Fermi's question about where all the aliens are?
I fear for the worst, that they're incredibly rare. And that
that's not the worst. The worst is that they're common and they always blow each other up or something like that, right?
I guess. Yes. Okay. And
okay.
They blow us up too, of course, which is another worry if we
right.
go too far in finding them. Yeah.
But it's not just exoplanets and life that we'd be looking for. I mean, we started off by talking about cosmology. So, what would these giant telescopes do for the working cosmologist?
Well, okay. So let me turn to the other aspect of telescopes, which is radio astronomy. So the advantage of doing radio is that you can penetrate the universe and see what happened before the first stars. So let me explain why that is. Galaxies are made of gas clouds that come together. And so these gas clouds are the building blocks of the universe. And we know roughly that they, each one probably must weigh 1 million solar masses, 1 million times the mass of the sun. And that's simply because you need a certain amount of gravity there for them to condense as gas clouds. And that's our best calculation of how big they should be. And so then you do this very simple estimate, which says, well, we know that our Milky Way galaxy is many billions of times the mass of the sun. That's its mass. Therefore, it must have formed from millions of these smaller gas clouds. They are the building blocks. That's the raw material from which we were made. And so how on earth do you find these things? Well, the idea is you look back in time before the first galaxy, before the first stars, and you look for gas clouds. Now, the way you would do that is you use the tool of the astronomers to measure hydrogen gas, which is a 21 centimeter line of atomic hydrogen. And so that can be excited and gives you an absorption or an emission signal. It's excited. It's the electron spin levels that are excited and de-excite, and so they give you an emission, or if they're excited, they will give you an absorption against something distant, some background radiation. So that's the idea. The trouble is, if you want to look at this radiation from way back in the past, it's highly redshifted. So from 21 centimeters, you suddenly have to start thinking about 10 meters, because that's roughly how far back you want to go to get to where the first clouds were that made the first galaxies. And there should be many, many of them. Now, you can't go back too far because you run into microwave background, and that sort of mixes everything together. But it's when the background radiation cools down as the universe expands, but the matter then cools down even further. And so you can see it as a cold shadow against the cosmic microwave background. So that's the idea. And the typical wavelength will be tens of meters. Okay, so that tells you what you're going to look for, a signal, a shadow against the fossil radiation from the Big Bang. But you can only do that in a place where the radio environment, the radio astronomical signals can get to us. The trouble is on the Earth, we have an ionosphere which surrounds us. You hear that when you listen into the radio, you turn between stations, you hear this crackle and pop, right? That's all from the ionosphere. And when you look at low frequency radio waves, 10 meter-ish radio waves, the ionosphere is opaque. Nothing can get to us from the distant universe. It just bounces off the ionosphere. So what do you do? Well, you go to somewhere where there's no ionosphere. So you go into space. That's fine. When you go into space, which we're certainly doing, the trouble is the Earth is a huge source of radio emission from things like FM stations, from cell phones, maritime radars, you name it. Space is not so simple if you want to look for this very faint signal from the beginning. So there's only one place that is nearby, not so nearby, but it's the far side of the moon. And it turns out the far side of the moon is the most radio quiet place in the entire inner solar system because the Earth just doesn't shine there in radio sense. Okay, so you're blocked completely. So our dream now, and it's more than a dream actually, is to put radio telescopes on the far side of the moon. Now, the first remark is that these are really simple radio telescopes. They're just like your TV antennas. I mean, nothing more. They're what we call dipoles. It's metal wires, basically, which you have to correlate together with wires or cables or something, and put the signal together, and then you beam the signal up to an orbiting satellite, which beams it back to Earth, for example. So that's the sort of thing we're going to start off doing. And if we have enough sensitivity, then that will give us a glimpse of the dark ages, of these clouds that were there before the first galaxies. And so that, we think, is the new horizon for astronomy. It's totally unexplored territory, the new frontier, if you like. We haven't been there yet. We're going to go there. And then we're going to learn amazing stuff when we go there.
Well, we do have these hints from JWST that there are galaxies that are younger than we thought and bigger than we thought. They assemble very early. And some people have worried or wondered whether this is a challenge to our models of galaxy formation. Do you think that that's a real worry or just like an inducement to learn more?
Well, I think the basis of all this, the problem with all of this, is that we do not have a theory of how stars form. And what we're looking at is the consequence of star formation in these very distant galaxies. So we based almost all our knowledge of star formation, what we measure in the Milky Way and very nearby galaxies, and to extrapolate that from our current vista point of 10 billion years after the Big Bang back to near the beginning, 100 million years after, is a really dangerous and toxic thing to do. You have no idea what we're doing, actually. So what we can do is observe, of course, and we do see things that seem slightly strange, far away, not what we had predicted. But I think at this point, the jury is out. We just don't know if this is due to some slight increased efficiency of making stars. Maybe there were more massive stars back then at the beginning of the galaxy. All these things are postulated. Or is it something radically new? Extra objects forming galaxies that we'd expected. So it's very dangerous to say that there is something radically new going on before you fully understand the standard physics, the simple explanations that we don't have by far not mastered at all yet. So all I can say about this is that we need a lot more data, and the data is going to come in the next year or two. And with all that data, we'll suddenly not have samples of tens of these galaxies, what we have now. We'll have hundreds, thousands, hundreds of thousands, and only then will we be able to come to a more definitive statement about what's going on back there.
You don't want to panic right away? You want to just collect more data?
Absolutely. It's panicking will, you'll be wasting your time. That's my...
Good. I mean, I think these are compelling cases for the exoplanets, high-resolution imaging and so forth, and spectroscopy, and also peering into the dark ages cosmologically. Before we move on to technology questions, are there other science targets that are especially appropriate for building facilities on the moon, whether or not in astronomy?
Well, here's the major science target, which is an extension of the Dark Ages search. Suppose we do go there. We're building experiments to go there, actually. There are one, two there already, which we'll come to. But suppose we start getting data from these many hydrogen clouds from the beginning. Well, the beautiful thing about this is there are so many of these clouds. I mean, when we do surveys of galaxies to get information about the size of the universe, the content of the acceleration of the universe, expansion and all this stuff, we're dealing with billions of galaxies, maybe. If we can start harvesting the data from the dark clouds, we'll suddenly be getting trillions of clouds in our surveys. Now, that means immensely more information, which you can then analyze to do cosmology with. And so our cosmology now is limited, as we said at the beginning, to 1 or 2% accuracy. But with all this, let's say 100,000, a million times more information even, we'll suddenly be able to get an accuracy that surpasses that by 100,000. I mean, fraction of a percent accuracy in determining the puzzling parameters of cosmology. So that's the dream. And there's one more aspect of this, which to me is even more incredible, is the only robust test of the inflation theory, is that the fluctuations from the beginning do have these primordial whirls and twists and things. That's common to all theories of inflation. This is not just the gravity waves, that's a whole other story.
Yeah.
But this is just intrinsic to the fluctuations. And the only way you can ever see those is when we have enough sensitivity. And so it seems to be true that with these telescopes on the far side of the moon, if we make them large enough, we'll have the sensitivity to actually pin down the details of whether inflation actually occurred or not. And we're able to test one of its, I think, most robust predictions, which are these what we call non-Gaussianities from the beginning.
Yeah.
So that's a goal for me, a major goal.
I guess I shouldn't pass up the opportunity while we have you here. I did talk to Adam Rees, our joint colleague, a while back about the Hubble tension, about the apparent disagreement between measuring the Hubble parameter using early things like the microwave background versus using more nearby stars and galaxies. Apparently, it's still a looming issue out there. Do you have a favorite prognostication as to what's going to happen? Is there new physics lurking there, or do we just have to get our measurements in order?
Well, I discuss this a lot with Adam, but let me just say that I'm very concerned that all the data that comes from using stellar indicators, supernova indicators, which Adam is the world's expert on, etc., it's a little bit like climbing a distance ladder to get to the things far away. And you can never be very certain about the first rung on that ladder. Yeah. It might be unstable, you might fall down, right? So now, many of us are completely certain it's a robust, very solid ladder, but nevertheless, it is an indirect way of getting far away. Ideally, what we'd like are what we call geometrical indicators, which don't rely on going up a ladder, but are just direct measures of distance. And I would say until we get those securely in place, for me, the jury is out, because there are worries just about the observational issues, the systematics that come from using exploding star supernovae and other types of stars to build your distance ladder. So I think we're still beginning to explore the natures of the environments of these different distance indicators. They don't all agree with each other. And I'm not convinced that we have a robust forward way there. I'd rather wait until we get some geometrical indicator, which will come in the next 10 years.
Okay, very good. Thank you for that update. So let's be much more down to earth. I mean, we're both theoretical physicists at heart, but in writing this book, I forgot to mention you've written a book. I will mention it in the intro, I promise. But Back to the Moon, The Next Giant Leap for Humankind. You must have dug into some of the technological challenges involved with literally going to the moon. I mean, you've already mentioned very briefly that you envision both human beings building things, but also robots building things. Is it going to be almost all one or the other? What do you imagine to be the mix of people and construction and so forth?
Well, it's such an rapidly evolving situation. I would have said a year ago that if you could do a lot with robots, but you need humans very close by to guide them, because a robot has to respond instantaneously. But what's happened in the past year has amazed me. That is the development of artificial intelligence at such an amazing speed. So now I do not quite see what the limits are, actually, of robotic deployment of telescopes on the moon, for example.
Right. So
Um,
basically, if you put a robot on the moon with a certain goal, we're more confident now that it could figure out how to solve puzzles maybe than we were a year ago.
that's right. How to, if it sees if there's a crevice in front of it, it might take seconds for it to get instructions from the Earth on what to do next. But I suspect before very long, we'll figure out ways of having, self-guiding robots that can cope with any conditions they come across. So that's what I think is an amazing area that's developing so rapidly. It's hard to predict where we're going.
It's easy for me in my brain as a very long-term science fiction reader to imagine robots building telescopes on the moon. Is that Do we really appreciate what the challenges are there?
Well, I think you need human intervention, right? Basically, because there are just so many surprises that you have to have someone on the spot to look out for. But again, I don't see what the limits are for the robots at this point. So remember, we're forecasting what's going to happen probably on a 20 or 30-year timescale for these big telescope projects. And the rate at which AI has developed so rapidly in the past 2 years, I mean, how on earth can we forecast where we may be in 30 years' time? It's all crazy. Yeah.
So what is the biggest challenge besides the fact that it's far away? I mean, obviously you're in vacuum, there's dust. There's no atmosphere, but there is dust, right?
Right. So let's talk about the dust. So lunar regolith is everywhere. It's very abrasive dust, actually. So it's not good for telescope mirrors. So we will need to think of ways to shield the mirrors somehow from the dust. Now, one interesting aspect is this, that the dust is photocharged by ultraviolet light and levitates, okay, because of the charge, okay. So it rises in the day, but at nighttime, it falls down. So
Really?
the
Okay.
hope is that in a permanently dark crater, dust will be much less of a problem, which is why you probably want to go there rather than some random place on the moon to build your telescopes. So I don't know. I mean, that's something we're discussing, and obviously there are also ways of self-repairing devices that can self-anneal, etc., to develop protection against dust too. So I think these problems are going to be surmountable by our engineers.
Have we learned a lot from the experience with Martian rovers?
That I cannot say. We've certainly experienced micrometeorite impacts on the Webb telescope already, and that has not been a major disaster. And one might expect similar issues on the moon. So I think we should be able to use our experience to cope with that too.
What about moonquakes? Are those an issue?
So moonquakes are known to be far, far weaker than earthquakes by an enormous factor. And so they're often caused by asteroid impacts or some minor settling of the moon, but they're relatively minor things. I don't think they're any danger at all. The one area where they've come up recently has been one of the first things we'll do on the moon is put down seismometers in various places. Now, Apollo did this, but we now have much better ideas and models for building seismometers. And the reason we want to do this is we want to measure the shaking of the moon, because that's basically like a gigantic gravity wave detector.
Ah,
So you can imagine right now we've measured gravity waves with basically having laser beams that are 4 kilometers long. Our future ones will have 40 kilometers long. We measure the shaking of these beams by a passing gravity wave from merging black holes. On the moon, 4,000 kilometers, you can suddenly do something different, okay? You can measure lower frequency gravity waves, just like longer to go distances. And you can measure the inspiraling of black holes that come together to give you the ones we've seen already. So it's a whole new chapter on gravity wave astronomy, which we'll do with seismometers on the moon and various devices based on them, etc., which we're planning to. And that's, again, fairly known technology, so it shouldn't be too hard. And I think that'll be one of the early things we do on the moon.
I had not ever heard that idea. That's a wonderful one. Is it clearly superior in some ways to just building satellites and bouncing lasers between them?
It's complementary. So right now, our best satellite, a main satellite project, has a separation of the satellites of 1,000,000 kilometers, you bounce lasers. So this is a very, very different frequency from the one you measure on the moon. So after that, we're debating formation flying of satellites with a few thousand kilometers separation. And that would be much more or less equivalent to what we do on the moon. So it'll be a complementary activity to what we do on the moon, actually, with satellites. Good. But that's a future thing too.
All right, so we've listed the moon is far away, it's cold, there's no atmosphere, there's dust, there's moonquakes. Is there any other worries that we haven't anticipated yet?
Well, you have to support people, of course, and we need them somewhere. And I think one of the big worries is going to be the physical state of people that suffer long stays on the moon. This is one of the reasons why we want to put them in a space station around the moon. So we've done that on the Earth, and I don't know how well people realize this, but when our astronauts come back from the space station after a 6-month stay there, if you probably have noticed, you see them in chairs. They are not able to walk very well.
Yeah.
And I'm not sure what other problems they may have, but on the moon, there could be longer stays, it could be worse. So I think we have things like this to learn from and understand much better. And of course, issues about radiation exposure, etc., like that. It'll all be far, far worse on Mars. Don't worry about that. The moon is an easy step forward. that people do. Mars, I worry about.
In the science fiction stories, our space stations always have rotation so they can mimic artificial gravity. But as far as I know, that's not in the plans of any current NASA program or anything like that.
I think that's right. That's right. You don't really want to do that for an orbiting space station, probably. Too.
Okay. And how much of the program of doing astronomy on the moon and other things is beholden to a larger program of getting people there on a regular basis?
So it's all part of the same story. So I think here is why I think we have to be patient. We have to realize that science, astronomy, telescopes are not at the head of the queue for the moon. But on the other hand, that gives them an enormous advantage because we're going to build infrastructure for the moon, not just the orbiting space station, but having lunar rovers, doing construction on the moon, et cetera, et cetera. And all of this will take some enormous budget, which is being planned. And it's partly spurred on by international rivalry.
Right.
Okay. Because it's clear that, if the US doesn't do this, China will, et cetera, et cetera. And it's not even clear where we're going. We have to have better coordination, of course. That's the whole of the story. But anyway, all of this will be very expensive. So if I were to imagine spending a few % of the cost of the infrastructure on science, that will be enough to build all the telescopes I've talked about. And the reason I'm confident of that is, let me give you an example. The space station and the shuttle were built at some, multi-billion-dollar whatever expense. And we would never have had the Hubble Space Telescope without those things, okay? Hubble was a few % of the total, right, that we put into all that other infrastructure in space. And you can make a similar argument for the moon. All the telescopes I've talked about will be a few % of the total of this amazing story that we're going to build on the moon and do things on the moon. So it seems to me it's not so crazy to imagine big science projects. That they're cheap, relatively speaking.
This is probably an unfair question, but is there any hope for international cooperation here rather than rivalry?
I think it's essential. Right? We better have this because even right now, I think we're very worried. NASA's very worried, for example, that they know the Chinese are putting science experiments on the moon. Probably, if anything, on a faster timescale than NASA is, although there's been the competition between the two. The worry is that, if the Chinese are there first, they say, I want this crater for my experiment. And that's a desirable crater. There aren't that many dark craters. There are of order 50 or something. I mean, who takes what? The choice real estate. I haven't also told you this, that these dark craters, some of them have immensely high rims. And those rims are always in permanent sunlight, because they're so high, they see the sun. So they're the places where you can pipe in solar power into your dark crater. Ideal for doing experiments, ideal for many other things too. There'll be intense competition for them. So I hope we don't resort to, I got there first, that's mine. We have to have coordination. We've done this in the past. The best example is Antarctica. I don't know how well known this is, but there are, I think, some 70 different research stations from different countries in Antarctica, all very nicely allocated, no rivalry, no wars. But we've done that. We know how to do this. Of course, the commercial stakes there are much, much less than what awaits us on the moon. So it's a different ballgame. But I hope we can have something similar to guide us.
Let's fill in a little bit the commercial stakes, because I'm interested in the motivation for private companies or individuals to go there also. I mean, we hear talk about mining, tourism, and so forth. Do you have a feeling for how realistic that is? Or what are the resources up there on the moon that you can't just get easier down here on Earth?
So the resources are this, that the moon has been bombarded by asteroids and meteorites over billions of years. And now this happened on the Earth too, but they burn up in the Earth's atmosphere. On the moon, they cover the surface with valuable raw materials. And so the moon has enormously larger reserves of rare earth elements like europium, vanadium, etc., that are essential for much of what we do on the Earth now in terms of high technology. From our computer screens to, windmills, whatever, all sorts of things. On the Earth, we're running out of supplies. We know that europium, for example, has probably 1,000 years of supplies left on the Earth. Other rare earths a little longer. But on the moon, we have enough to keep us going for 1 million years. Thousands of times more resources. And so it's an incredibly interesting target for the mining companies. You know that as resources get lower, the price goes up, so it's going to become incredibly expensive soon on the Earth. What is more, it's even worse than that, because mining rare earths is a really toxic process. And right now, China dominates the rare earth industry. Mostly for that reason, they would take the risks. Now, it's not clear, and they also have the dominant reserves on the Earth. So there are two reasons there. So going to the moon will open up new possibilities for mining. It will be something that will last for thousands of years. It'll be a major investment. And it's such an incredible attraction for the big mining companies that I think that we're going to do that regardless.
Yeah.
But before we mine on the moon, we have to survey the moon. And that involves a whole other story. But that will be what's going to be happening in the next 10 years, choosing the best mining sites on the moon.
I guess maybe I just have trouble imagining this, but how do you ship all that stuff back from the moon to the Earth? That sounds very expensive.
Well, not really, because right now we're going through this dramatic leap in space cargo development, where we have many launches at the 110 level capacity. We're in the process of building two. One has flown successfully, the NASA SLS. The Starship has not yet flown successfully, but both will have of order 100-ton payload. And what is more, Starship, when it does eventually work, will be unlike the NASA spacecraft, recyclable, reusable,
Yeah.
which is going to bring down enormously the payload cost. So I don't think that's going to be a real problem. We'll be able to, over the next decades, have efficient ways of shipping whatever we need back to Earth. There'll be some price attached, but it'll be nevertheless a source of enormous profit for the mining companies in principle.
So if you had to guess, you don't have to, but if you wanted to, when would you anticipate the first telescope seeing first light on the moon?
Well, actually in 3 years' time.
Okay, good.
So let me explain that. So not necessarily the most useful first light, but this is a radio telescope. And so two projects are under planning now to go up in 2026. One of them is a single antenna. It's designed by NASA, the Department of Energy, and it will go on the far side and will look for the shadow of the dark agent. So that's the first thing we're doing. A simple dipole antenna on the far side of the moon. The Chinese already landed something on the far side, the first such antenna, but it didn't bring back data because the local electronics was so noisy, it was designed badly, they didn't mask that out. But the new instrument built, in this case by NASA, will solve that problem. The only difficulty is that it'll go to the far side, they'll land it there, but its battery power is limited. So it doesn't have large enough batteries to survive more than one night on the moon, which is 14 days long. So the problem is that it won't get enough data. So we have to develop power, battery power, and we're not quite there yet. Meanwhile, on exactly the same timescale, the Chinese have solved this problem. So they're sending a flotilla of 9 spacecraft to orbit around the moon, one mothership and 8 smaller antennae, and they basically orbit the moon far side to near side every 2 hours. So they take their data on the far side, they fly in formation, so they act together like an interferometer or a giant radio telescope, and they take their data, then radio it back to Earth. So that, it seems to me, has the best chance of getting the first science signal from the far side of the moon, and that's going to happen soon. And then on the longer time scale, we have much more dramatic projects. In radio astronomy, we know we'll need much more than 9 antennae. We'll need hundreds, maybe even thousands. And so we're designing projects to do just that on the far side of the moon, but that's going to take much longer, of course.
I love the idea of the simple, cheap, fast radio telescope, because once there's any working model, it becomes much more real in people's minds, right? It will help inspire them to the next step.
Exactly, that's right, and that's the beauty of one of the current NASA programs, where they have commercial spacecraft which carry small payloads, and they've been able to sell projects to other countries. That I mentioned there was an Israeli project, a UAE project also, and they'll be continuing to land small lunar rovers in these cases on the moon. That's their immediate goal. India is very much involved too. They want to do surveying of the moon with their next generation of lunar orbiters. So it's a huge and interesting competition now.
It's interesting how it comes and goes. It was 50 years, and then we went quiet, and now we're back again. It seems like with earnest. But I mean, maybe for the very last question, let's reflect a little bit on how the scientific community goes about things like this. I mean, these are obviously very big, ambitious goals that you were discussing here. I worry that sometimes scientists are almost too cynical in an attempt to be realistic. Like they hear these giant plans, and of course, if you're the one proposing them, you'll be very enthusiastic. But others are going to be like, that's a load of hot air. We'll never get there. How well does the scientific community do in coming together over these big plans, and are there ways we can do better?
Right now, I would say the scientific community is doing a slightly better job than our political communities in planning for experiments on the moon. We have conferences in which participants include different space agencies, not just the US, but also I was one recently with both China and India very well represented, describing their projects for lunar astronomy on the Vostok. So all of this is happening. I think overall we still need better coordination internationally to make sure that when the commercial aspects which are driving all of this really get underway, there is some suitably peaceful strategy for negotiating, for sharing, international coordination. Right now, we don't have that. I think we have a window maybe of a few years to develop this. As the political situation improves, perhaps we'll get there. Right now, it seems impossible to imagine this happening, but I'm optimistic. What we want to do is avoid the Wild West, basically, on the moon. That's the hope somehow.
I think it's good to be optimistic about these things. Certainly, it's an ambitious program, and I'm very excited about everything you've told us. So, Joe Silk, thanks very much for being on the Mindscape podcast.
It's been a real pleasure, Sean. Thank you.